Hi everybody, this is the Math 31 optimization review, and this is question 11. Here's another question that you might recognize from before, probably the Math 30 course here. So a rectangular open-top box has been made from a piece of material 18 by 48. Okay, so what we're doing here, what this is describing is, here's our 18, here's our 48, and what we're going to do here is we're going to be chopping out corners out of this. And then we're going to be folding along these dotted lines to create this open-topped box. Now, it doesn't have to be an open-top box. We could cut this so that it was a little different here. But anyway, this is what it's describing. And we don't know how big these pieces are supposed to be. What we're interested in is knowing the relationship between the volume of this box, okay, and the size of those squares that we're removing here. Now, what we need then is some way of relating the volume to those pieces there. Well, the length of the box is going to be 48 centimeters, okay, minus 2 x's, okay? 48 centimeters minus 2 x's. I'm going to see it this way, 48 minus 2x. I'm going to come in x on both sides here. The width of the box is going to be 18 minus 2 x's, okay? So this distance right here is 18, and then we're coming in an x on either side. And then remembering that we're going to fold this part up, we're going to fold this part up, okay? And each one of these little tabs here has a length of x. That means the height of our box at the end here is going to be x. So volume is going to equal length, width, height. This will equal 48 minus 2x, okay, times 18 minus 2x times x. Now, this is one of those places here where, you know what, I would probably be a little bit more tempted at this point here to expand that out. Just because I've got 3 terms multiplied together, I don't know if I want to go through the product rule for 3 terms here. So 48 times 18 will be 864, and then there's going to be an x tacked on at the end. And then I'm going to get minus 96x squared minus 36x squared plus 4x cubed. Okay? And so now putting this all together here, 864x, what do we got here? 96 and 36. I'm just going to do that on a calculator real quick just because, whoops. See, I wanted to make sure I didn't make a mistake, and then I still put down the wrong sign. So it's going to be minus 132x plus, sorry, x squared plus 4x cubed. Okay. Now, if we take the derivative of volume with respect to x, we'll get 864 minus, what are we going to get? 264x plus 12x squared. Now, there's our derivative. Okay. I'd probably be tempted to turn that around and put it in the right order, but I also want to set that equal to 0 because we're going to optimize this. Now, this is a little bit more confusing here. I want to maximize the area here, or the volume, but what we're getting here is a cubic. And if you think back to the way a cubic looks, okay, well, a cubic has got a local max and a local min to it. So I got to be a little bit more careful with this one, that I'm finding the right value here. Okay, so let's take a quick look here. Let's see if we can divide those things by 12. That would be wonderful if we can. Okay, so 864 does divide by 12. Does 264 divide by 12? That would be fabulous. Oh, it's almost too much to hope for, but it does. X squared minus 22x plus 72 is equal to 0. And let's just take a quick look here. 72 divided by 18 is 4. So this is actually going to factor down really nicely. This is going to end up being minus 18 minus 4, which means my 2 solutions here are going to be positive 18 and positive 4. Now, only one of those is going to give me the maximum here, but there is a way that we can kind of think about this. And I really am a big believer in us taking advantage of material that you already know. I know that this is a cubic. Okay, I know that this is a cubic that goes up. Okay, so a cubic that goes up is going to look like this. Okay, which means the very first thing that we're going to bump into is going to be our max. And down here, the second extreme value here is going to be a min. So that tells me that the max is going to happen where at the 4, and the min is going to happen at the 18. So I don't want that. So what I'm interested in here is the maximum volume here, and that's going to be where x is equal to 4. Now I could have done that a slightly different way, looking at the intervals of increase and decrease along the derivative. Okay, and I mean, if you want, I can take a look at that real quick right now too. I know that this is a parabola that opens up. Here's 4, here's 18. Okay, parabola that opens up. So it's positive, so it's increasing and then decreasing and then increasing. So on either side of the 4 is increasing and then decreasing. So again, that makes this a max, and then it makes the 18 if you follow it through a minimum. So regardless of how you look at it, the size of the square that we're plugging out here is 4 centimeters by 4 centimeters.